Hey everyone, welcome back to Bon Science. Today we'll be going over Unit 2, Topic 6 in AP Chemistry, which is called Resonance and Formal Charge. So this unit this topic builds off what we did in the last episode with Lewis diagrams, but it's going to introduce us to some more advanced concepts, so let's get straight into it. So the first concept we're going to discuss today is resonance, spelled exactly how it sounds. Resonance, just like that. So resonance occurs when there is more than one valid way to draw a Lewis diagram. So a really good example of this is NO3 minus. There is more than one valid way to draw the Lewis diagram for NO3 minus, which is nitrate. So if we just count our valence electrons for NO3 minus, we have 6 times 3 from the oxygen, 5 from the nitrogen, and then 1 extra from the charge, so we have 24 valence electrons. So if we were to take a look at this Lewis diagram, this is one possibility, right? And I'm not going to draw the lone pairs in, I'm going to leave those for you guys to fill in, but it's pretty self-explanatory. It's just like putting in the lone pairs to fill it out. Actually, I'll draw it in, I'm not lazy. Just looks a little messy, but roughly this is the Lewis diagram, right? Brackets and then the minus because it's an ion. Now, the thing is, this is a completely valid Lewis structure, right? It obeys our octet rules. We have everything with a full octet, everything has its lone pairs, we have the exact number of valence electrons, that's fine. But let's say I chose to draw the diagram like this instead. Let's say I put the double bond on that top left oxygen instead of the top right oxygen. If I do that, I just put an extra lone pair on that, didn't I? If we do this though, let me delete that lone pair. But if I draw it like this, and then the bracket and the minus, obviously, is there anything wrong with this? I mean, there's really not, right? We've used 24 valence electrons. We have everything with the full octet, so it's a completely valid Lewis diagram, and it really is. So the question is, what do we do when we have instances where we have more than one valid Lewis diagram? And that's when you have resonance. Resonance is this phenomenon where there is more than one valid Lewis diagram, and when there is resonance, you have to draw it a specific way. So the way you draw resonance is you are going to draw all the possible Lewis diagrams. And actually, there is a third way to draw it if you are astute with these. So let me try to get some space here because these are kind of big. I'm going to draw this one really small. But if you think about it, this is also a completely valid way of drawing it, right? Put the double bond on the bottom oxygen, right? With your lone pairs on the other ones, you'll be chilling. Completely valid. So in the case of nitrate, we have 3 valid structures. And so the way you draw resonance is you're going to draw all your possible structures, so in this case 3, then you put some arrows between them, usually like this. And usually on the paper you have space to draw them all in a straight line, but I don't have enough space for that here. So I draw the arrows like this, but you just want to draw these arrows between all of them to show that all of these are possible Lewis structures, right? And that's how you draw resonance. It's annoying because you have to draw all the possible Lewis diagrams, but it's really not that bad. You just have to make sure you've got all those combinations down, right? But that's basically resonance in a nutshell. Now, the next little subsection I want to discuss here is exceptions to our Lewis diagram rules. So in the last episode, you remember that we covered the rule that every atom needs 8 electrons to have a full octet, and that no atom should have more than 8 electrons because they can only have an octet. That's not exactly true. The first exception I want to go over is boron, which is B on the periodic table. It has 3 valence electrons. So it's very close to the top of the periodic table. It's in your second period. Now, boron is weird because it is satisfied with only having 6 electrons. It doesn't need a full octet, it only needs 6. So a very good example to demonstrate this is BH3. It's a compound we have 6 valence electrons total, because we have 3 from boron and then 3 from the hydrogens. And so when you draw this Lewis diagram, you can just draw it like this, and boom, you're done. You might be thinking, well, boron only has 6 electrons. How is it satisfied? It's because boron only takes 6 electrons to be satisfied. And it has 6 electrons here from the 3 bonds, right? And so boron is completely chilling here. So if you ever get a Lewis diagram with boron in it and the boron only has 6 electrons, that's what's right, because boron only takes up to 6 electrons. Now, the other exceptions you should be aware of are expanded octets. Expanded octets occur in the 3rd energy level or lower because those atoms in the 3rd energy level can start stuffing electrons into the d subshell. Because if you remember, the d subshell, it technically starts on the fourth period, but remember that the d subshell is 1 energy level lower. So on the 4th period, you have the 3d subshell. So on the 3rd energy level. So when you get into the 3rd energy level, you have some atoms that can put some extra electrons into that d subshell on the 3rd energy level. So a really good example of this, SF6. So sulfur is on the 3rd period. So it could have an expanded octet. It doesn't necessarily have to have an expanded octet, but it could. And if we draw the Lewis diagram for this, I'm going to skip like the steps. I'm just going to straight up draw it, and I'm going to assume you guys can follow along with it. But if you do draw the Lewis diagram for this, it ends up looking like this. And obviously sulfur has way more than 8 electrons here. It actually has 12, but that's okay because it has an expanded octet. Now, expanded octets usually hold either 10 or 12 electrons. It doesn't usually go more than that. So you're either going to have 10 or 12 if you have an expanded octet. You're not going to have like 14 or 16. That's too much. It goes up to 12 at most, right? And sulfur has 12 here. So if you ever have a Lewis diagram and you have some extra electrons and you don't know where to put them, you should really like stop to think and be like, okay, can this atom expand its octet? And if it's in the 3rd energy level or lower, the 3rd period or lower, it can expand its octet. So stuff like sulfur and phosphorus or xenon, those are all very common ones that expand their octets. But if they can't expand their octets, you can stuff some extra electrons in there, and it's a completely valid Lewis diagram. Now, the last concept I want to talk about is formal charge. And formal charge it's a quantity used to describe the charge on an individual atom in a Lewis diagram or in a covalent bond. So what I mean by that is when we're calculating formal charge, it's done in a very specific way. So let's draw the Lewis diagram of H2O, water. This is what it looks like. So every atom in H2O has a formal charge. So this hydrogen has a formal charge, this hydrogen has a formal charge, and this oxygen has a formal charge. And the way you calculate it is you do valence electrons minus assigned electrons. Now, valence electrons is very self-explanatory. It's the valence electrons that that atom normally has. So let's calculate the formal charge on oxygen. It would just have 6 valence electrons, because oxygen has 6 valence electrons. Assigned electrons is a little more tricky. To count assigned electrons, you count each electron in a lone pair as an electron, and then you count each bond as 1 electron. So what I mean is oxygen has 2 lone pairs, or 4 electrons. So you have 4 assigned electrons from there, but it also has 2 bonds. Now, even though each bond is 2 electrons, when you're talking about assigned electrons, they only represent 1 electron. So you have the 4 electrons from the lone pairs, and then you have 1 electron each from the bond, which sums to a total of 6 assigned electrons, which gives you a formal charge of 0. So that means oxygen has a formal charge of 0. If you wanted to do it for hydrogen, you would have the 1 valence electron from hydrogen and the 1 assigned electron from the bond, and you would get a formal charge of 0. And that's the same for both hydrogens, right? So the formal charge on every atom in this water molecule is 0. Now, that's the easy part of formal charge, because formal charge is a very important application that you need to be aware of on the AP exam. And basically, formal charge can be used as a way to verify the validity of Lewis structures. So let's look at SCN minus. So there's a couple of different ways that could theoretically be valid for drawing SCN minus, and I'm going to draw them out right here. So one way we could draw it is like this. And if you don't believe me, we have 4 valence electrons from carbon, 5 from nitrogen, 6 from sulfur, and then 1 more from here, so that gives us 16 valence electrons, and then we have 2, 4, 6, 8, 10, 12, 14, 16 here. So that's one way. But I could also draw it like this. And if I really wanted to, I could also draw it like this. These are all potentially valid ways of drawing it. There's really nothing wrong with any of these structures on like face level, right? Everything has a full octet, we've used our valence electrons, and we're good. But the truth is, not every possible Lewis structure is valid, and you have to use formal charge to check it. So there's a couple of rules with formal charge. So the first rule is formal charge should always equal -1, 0, or +1. And the second rule is that the most electronegative, so I'll just say most electronegative element should have the negative formal charge. So here's how this looks. Basically, if you have a bunch of valid Lewis diagrams, you should check them for formal charge, because sometimes the AP asks questions where they throw you these Lewis diagrams and they all look correct, and then they're going to ask you which one is the most valid Lewis diagram. And the way you tackle those questions is like this. You're going to calculate the formal charge for each atom in each Lewis diagram. So let's start with this one. So in here, sulfur we know has 6 valence electrons, and in this diagram it has 5 assigned, 3 bonds and then two electrons in the lone pair, so this is its formal charge. It has a formal charge of +1. So we can give it a formal charge of +1. Carbon has 4 valence electrons and then 4 assigned electrons, so this has a formal charge of 0. And then nitrogen has 5 valence electrons, and in this diagram it has 1, 2, 3, 4, 5, 6, 7 assigned electrons. So that gives it a formal charge of -2. Now remember, formal charges can only be +1, 0, or -1. So immediately this structure is invalid because of that formal charge of -2. So we can forget about it. It can't exist. Alright, so let's talk about the next one. So in the next one, we know sulfur has 6 valence electrons, and it has 1, 2, 3, 4, 5, 6 assigned electrons here. Carbon has 4 valence electrons, 4 assigned electrons is 0. Nitrogen has 5 valence electrons, and then 1, 2, 3, 4, 5, 6 assigned electrons, so its formal charge is -1. Okay, that still looks valid, right? All our formal charges are -1, 0, or +1, so we're chilling. But let's check the other one. So here sulfur has 1, 2, 3, 4, 5, 6, 7 assigned electrons, and then we know it has 6 valence electrons, so its formal charge is -1. Carbon has 4 assigned, 4 valence, 0, and then nitrogen has 5 valence, 5 assigned, so that's a 0 formal charge. So at this point the question is, okay, well, these both have valid formal charges, so which one's correct? The answer is the Lewis diagram where the most electronegative element has the negative formal charge is going to be the valid one. So nitrogen is the most electronegative element, right? It's more electronegative than carbon and sulfur, so we know it has to be the one with the negative formal charge. So that means that this is the valid Lewis structure, because this is the one where nitrogen has the negative formal charge. So that would be your answer. If they asked on an AP which one's the most correct Lewis structure, it would be this one, because this is the one with the most valid formal charges. And that's formal charge. Now, one last thing I want to discuss is bond order on resonance structures. So in normal Lewis diagrams, bond order is literally just directly a function of how many bonds there are. So 3 bonds is a bond order of 3, 2 bonds is a bond order of 2, and 1 bond is a bond order of 1. In resonance structures, it's a little bit different. If a question asks you the bond order of a resonance structure, the way you do it is you count the number of bonds. So in all our resonance structures, we have 4 bonds, right? And then you count the number of bonding sites. So bonding sites just means areas where bonds form. So we have 1 bonding site here, 1 bonding site here, and 1 bonding site here. So we have 3 bonding sites, and you just divide those two, like I'm doing right here. You get 1.33. and you get this kind of decimal bond order. It's a little weird, but you should know how to do that because the AP does like to ask about this. So if you're asked about bond order on a resonance structure, go through this format. Don't just be like, okay, this is a bond order of 1, this is a bond order of 1, and this is a bond order of 2. That's not how it works. You have to go through this process. If it's a normal Lewis diagram, you can just count the number of bonds and you're chilling. But if it is a resonance structure, you're going to have to do this process. But that's all I have to discuss today. I hope you guys enjoyed the video. I hope that all made sense. This is a bit of a doozy, but at least we got it out of the way now, and I'll see you for the next one.